Yep. Thank you very much. Well, goodness, how does one, it's quite an honor to end such a meeting, to be the final talk in such a meeting. And thank you so much, Jan and Tiziano, for the very kind invitation to join you all here, and to all of you for the conversations that we've had. And I feel very privileged actually to have been able to sit and listen and put faces to names and learn more about the techniques for chronology that I'm not so familiar with. So I also have an apology, because I know that several of you have heard versions of this talk a couple of times before now, and I have tried to mix it up a little bit, but I do apologize for duplication. But in view of the presentations we had yesterday from Sturt Manning and from Malcolm Weiner, of course, we again saw these two different positions argued for the dating of Thera, and the work that I've been doing really does, I think it brings something to this picture. So I wanted to have the chance to sort of talk about this again today. So I will get on with it, and I will launch in with just a very simple start, the very basics of what I do. I trained as a geoarchaeologist. I got interested in tree rings because of the chance they give you for chronological precision that is beyond what other techniques can offer. So, and a lot of the work that I do now with radiocarbon is really built on this very simple fundamental process of tree ring dating, where we are able to get a secure calendar date from a living tree. We measure our tree ring pattern, and then we pattern match backwards through time from successively older samples. And so it's very, very simple to build these well, it's also a lengthy and a lifetime's process, building these master chronologies of tree rings for different regions. But once you have that, there's a lot that you can do with it, from looking for markers in these dated sequences of traumatic effects like droughts, like floods, like fires, and like volcanoes, as you see up there, to using this as a proxy to reconstruct exact patterns of rainfall, temperature through time, to finding chemical and isotopic markers for events like hurricanes, for human pollution, for volcanoes, and then finally to the radiocarbon, because of course every single tree in its respective year is taking in carbon-14. And so right now, all of us and all of the trees out there have something in common. The tree ring forming this year has the same amount of radiocarbon in it as we have in us at the moment, and we're all in equilibrium with our environment. And as soon as those tree rings stop growing, then they're going to start decaying. And so because we can independently date the tree ring record, it allows us to create this calibration resource where we can reconstruct what radiocarbon patterns were like in the past. So that's our 14C in tree ring years. And as you know, the calibration curve previously in Cal 13 and still in Cal 20, I need to sort of emphasize that the majority of the Holocene still in Cal 20 is based on decadal blocks of tree rings, 5-year blocks of tree rings, but this is improving. And it's improving fast. But initially in Cal 13, you've seen a version of this in a couple of other presentations, is based on these decadal blocks. You can see how the curve is drawn through the middle of that scatter of points. We've now got in Cal 20, the blue curve, and you can see that this has changed the structure of the curve. And I've had a couple of lovely conversations with Bernie, with Tiziano, and we've talked about how so much resources have been put into the Thera period to make this change in the curve, and how this can really be a model for something that we look at in lots of different time periods, because we have the classic problem of this radiocarbon plateau, and it occurs time and time again throughout time. So we can use Thera in lots of useful ways to inform our studies of all different time periods. So this is how Cal 20 looks now, replacing those decadal blocks of tree ring data with single year tree ring data. And these are data from multiple different radiocarbon laboratories, and also from different trees. So we have the original Irish and German oaks represented at annual here. We also have things like bristlecone pine and another conifer species recognized in here. So within this scatter of data, which is the realistic picture of Northern Hemisphere 14C and what it's actually doing in this time period. And look at how wide-ranging and scattered it is when you reveal it like this. We have laboratory offsets, and we have some slight species locational offsets. And what we were able to learn through looking at these data is that there's, by looking at trees from different growth locations, run at different laboratory, run at the same laboratory, we have a control there. We can measure the exact regional offset. We don't need to speculate or place a single data set against InkCal anymore. We can say, right, well, we know what the oak's doing, we know what the pine is doing, and we know there's a 6-year offset between those two. We also know that's incorporated within InkCal, and some of the error that you see within InkCal is designed to take some of these uncertainties into consideration. Okay, so this is that curve. And I just wanted to show you that if we extend down this direction currently in Cal 20, the data is even thinner on the ground, okay? And I could go in lots of different directions, but I'll go sort of backwards a bit. No, my backwards one is gone. Even thinner on the ground, right? So the good news about this is that thanks to the Malcolm H. Wiener Foundation, 12,000, we've got all of this new annual C14 data is going to be brought in. It's going to augment the next version and the version after that of the InkCal calibration curve. The current aim is to try and have a new InkCal out next year. It might slip into the year after, but there is a push to get one out soon. So, and we'll try and get as much of this data into it as we can. So that is the good news. It's also, there are downsides to having a curve constructed with this high resolution data. The good thing is it's the very best that analysis will allow us to create at the moment. The bad news is you're still not going to get rid of plateaus, and there's still going to be a problem. And the structure that you get may mean that you get a whole, different calibration issues. So you get by these multimodal sort of positions for your data. So I just want to draw your attention to this. It's a really good one to keep in mind. It's a recent radiocarbon into comparison study, and it talks about the state of the art. This is the best we can do. If we send the exact same tree ring to 30 labs and we get them to analyze it, and then we compare the result that 30 different labs get on the exact same tree ring for the exact same year, what we find is that even for the very kind of the best of labs, the best agreement shown is plus or minus 10 years. And so you have to keep that in mind. We have a calibration curve now that is based on data that's been very carefully vetted, and larger offsets are avoided, but still any data that you put against the curve is going to have associated errors of some sort, be they regional, be they laboratory based, and 10 years can actually be quite a significant difference. And so we know that with Thera, we've got, I think, sort of 300 or so data points from annuals across the Thera period. And we've seen that these can be modeled in a variety of different ways to result in a date range that is sometimes quite precise. But I'm really cautious about annuals when I look at a plateau like this, and I know about interlaboratory variation. And so for me, I want something with more certainty. A model is speculative. You make decisions about how you put your model together, and we all do that, and we have to do that in order to interpret the data. But I worry about annuals in this context because of this plateau effect. If you take secure stratigraphic contexts for Thera, and you look at the sort of the youngest level, the sort of lower representation for the result, this is kind of an average for stuff that's coming out of Theran context on the mainland and on the Thera itself. And you can see it's slap bang on the plateau. We have a volcanic eruption right on a radiocarbon plateau. And it's always going to be difficult. And several people have said this as well. And Walter Kuchera has written about it. It's almost impossible with what we have. It is impossible to get a precise exact calendar year date for Thera using the data, the radiocarbon data that we have right now. So I'm bringing up the controversial olive, and you'll all be really familiar with this as well. And it's the one thing about this olive. And as a dendrochronologist, someone who studies tree rings, what I like about this olive is this is the inside of it, and it is 100% definitely, certainly older than the outside edge. And that's a certainty. Now, I like a certainty, because there's no room for maneuver. I'm not having to speculate about that. It's a certainty. So when I model this, we have estimations of rings, growth boundaries. We know from recent studies, I'll show you how these calibrate out, but we know that these boundaries can be really not representative of annual growth. And so it bothers me, because as soon as we start calling these years, then we get into speculation. But on the other hand, there is a validity in trying to use all the information you have to get the best result that you can. But anyway, I just want to show you, I model this as a simple ordered sequence. I just go with what I know. The inside is older than the outside, and that's definite. So that's how I do my models for this. And just to show you, this is how it looked for the endmost portion of this olive, done on the wiggle matching of a simple sequence to INCAL 13, it looks like that. And so you get, this impression of a very, very precise range, but in fact, it's not accurate because the calibration curve wasn't as accurate as it could be. And then we move on to what it looks like now against INCAL 20. And this kind of illustrates one of these, more problematic aspects of having more structure in the curve, that you get these kind of three options that come up in the probability distribution. But these probability distributions are so mobile. And I'll show you an example of that in a minute. But just in case you're not familiar with these papers that came out on olives in the last couple of years, are really nice informative studies on how olive grows. Hopefully all of you looking at that would agree it doesn't look like an oak or a pine, in that you can't see very clearly defined tree ring growth. And also notice that some areas from just under the bark radiocarbon date really differently to other areas just under the bark. And this actually isn't unusual. I can think of a few other species of tree where we know this happens. You kind of get cambial, the edge of the tree sort of stops growth in one area of the tree and it continues growth in another area of the tree. So we have to be, even though, we're kind of trained to, has it got bark? It's got bark, great, we'll get a cutting date for that if it's dendro, or, this is the best place to sample if we're doing radiocarbon. If you're looking at a plant like this, where you can have this dieback effect, then not necessarily. So we have lots of really good critical thinking about this olive, and also again making this point in this paper that depending on the decisions you make as a person modeling this using Oxcal, if you're using Oxcal, you can put this probability distribution anywhere in the 16th century, and it's subjective. To show you the impact of a 10-year offset, here is my ordered sequence model for the Santorini olive, just those 4 pieces. Simple ordered sequence. That's what I get. Very widely spread across the plateau. If you add just 10 years to that, and remember that is the current level of our limit of our range in terms of interlaboratory uncertainties, you can see that then skews back into the 17th century. And then if you just minus 10, then you're moving right forward. And so I'm saying be careful and don't jump to conclusions, and be open to all of the possibilities until somebody finds an oak or a juniper buried under the ash, and then we'll be in business. Then we can really do some wiggle matching and get a very precise date that way. Until then, let's go back to the tree rings, and I'm going to talk about the work that I've been doing, having got frustrated with radiocarbon not being sufficient to ever get a very precise date for Thera. I go back to what I know, which is best is the tree rings, and this is growth disturbance in bristlecone pine, where this tree has been growing in the White Mountains and a volcano has erupted, and the volcano's put out a layer of sulfate. The sulfate backscatters the solar radiation, and it causes sudden and short-term cooling, and that has the effect of freezing the sap in the cells. It blows apart the cell structure. I've moved on, but that sort of damaged-looking cell structure, and so it leaves a permanent marker. And what is really interesting and exciting about that is that my colleagues in the ice core community, working with bands in the ice where they have layers of sulfate. So as that aerosol goes around the globe, the sulfate will lay out on the ice, and you have these bands of chemistry that are directly linkable with the volcano. And for the last 2,500 years, this relationship between tree ring growth, and this is actually not just bristlecone pine, but it's a whole range of different tree rings showing markers for these sudden volcanic events, have been correlated with the northern and southern hemisphere ice records, and they show a very, very, very strong correlation. So for the last 2,500 years, we're really certain that where we see these markers in bristlecone pine particularly, we can be pretty certain there's a volcano. But of course, we always have to be careful because there are other things that can cause a sudden short-term difference in climate. And a tree ring doesn't chemically link with a volcano like an ice core does. So we're relying on correlations. And so that's something to be careful of. But back in the 80s, the first ever association of a tree ring with a volcano was for this event in 1627 and 1628 in the Irish Oaks. And actually, these two papers are the reason I got into dendro and did a PhD in the first place, because I was so excited by the fact that two trees on opposite sides of the world could be showing that something on a global level happened, and they could be showing it to within 1 or 2 years of precision. And at the time, everyone was saying, within the tree ring and the radiocarbon community was saying, well, this could be a candidate for Thera. And I think there's lots of lessons in the unfolding story, not just in how we use that radiocarbon data for Thera, but also how we look at all these lines of proxy evidence and radiocarbon evidence and archaeological evidence, and the coming together of different perspectives as we sort of move forward. So this is my colleague. I'm going to tell you about a study that came out this year. And this is my colleague, Michael Siegel, who's a co-author on the study. And this is a bristlecone pine sample. And these two funny lines here are showing you two of those frost events. So if we zoom in on those, that's what they look like. They're this disturbed cell structure. And what that's saying is these bristlecone pines experienced two mighty volcanic eruptions in this year and in this year. And Michael was working on looking at the different ice records. So prior to this coming out, we have a situation where we have in Greenland, there've been multiple cores taken through the Greenland ice. And all of those cores had been dated on slightly different dating schemes by different groups. But within them, they'd measured for volcanic sulfate, and they'd found these spikes of volcanic sulfate. And what Michael thought was, well, what about, you've got those two markers in the trees and they're 26 years apart and they're very dominant. They suggest two volcanoes, big ones, high sulfate producing ones, 26 years apart. And so we went looking for those patterns within the sort of ice core schemes, and we're able to align the whole of the Greenland record, which is here. And then we moved to Antarctica. And this is the Antarctic record. Now, the Antarctic record, they just got a new sequence out, and it's very high resolution. It's almost annually resolved. It's a very good, clear sampling. So what we have here is a global now picture of volcanic sulfate in the Thera period. This was the aim, to see globally, what is the record of volcanism? Where do we have evidence in time through these methods for volcanic events? So this is how we started out. We were fortunate that when we sampled this event, this is the 1626, 1627, 1628, depending on which record you're looking at. This is the one that was for a very long time associated with Thera. And we were lucky because we found volcanic ash, we found tephra in the volcanic sulfate, and we were able to chemically analyze the tephra, and it's an exact match for Aniakchak 2, which had been suggested. And we were able to confirm it in this study because we did very high resolution sampling. We pulled that tephra out just before the stratospheric sulfate, and we were able to show that there was not two eruptions, there was just one. It was very high sulfate, and it is Aniakchak 2. And that's good because it completely rules that out for everyone for Thera. So we don't have to argue over 1628 anymore because it's Aniakchak 2. So we can say that's not Thera. And I think I can say that without anyone being upset. I know for a long time, the archaeological community would say, well, of course it's not Thera. That's what we've been saying all along. And equally, this one, that's not Thera either, is it? Nobody thinks that's Thera anymore. So that's great. So we can rule those two out, and that gives us a list of dated volcanoes globally in the Thera period. So what we've done here is we had the exact dating for these two big spikes, and then we've got other tree ring marker events, and Malcolm mentioned this one at 1524, and I'll talk a bit more about this in a minute. These have all been observed in tree ring records, but they're not as strong or as clear, any of them, as these two. But actually now with the sulfate, that's not at all surprising. In fact, that's exactly what you'd expect, because the big sulfate is what causes the strongest tree ring marker. So where next? Which is Thera? Good question. We don't know, but at least we can offer you dates, and then you can look at your data and you can decide which one aligns best with your data. But in the meantime, we'll work to eliminate some of them. So I'll show you what I think in terms of elimination. First of all, though, I will just say, some people have asked, the question of how much sulfate Thera produced is a really big one, because how much sulfate Thera produced directly impacts how much of an effect it had on climate. And there's a wide range of estimates. We don't exactly know, because the only way to understand how much sulfate Thera produced is to know which of those acidities in the ice it is, and then you measure it in the ice and you get an exact reading. The other way is to use the tephra and get the information from the petrologic analysis, which is difficult. But the work that has been done on petrography suggests that Thera is much lower in sulfate than Tambora. So this is one of David Pyle's papers from very early on, where he's saying, actually, look, here's Tambora, and look at that. Look how different those values are between Tambora and between Thera. And there's a couple of other studies like this. So actually, for Thera to be low sulfate and for it to be one of those 16th century low sulfates is absolutely, again, what you would expect. And actually, the data has been out there for a while. And you can see, looking at these, these are all significantly smaller than these two. And I'll show you a comparison with Tambora in a minute. But the other thing we can say about Thera is that it was very big, it was very explosive. And so even though it would have had a small amount of sulfate, because some people have said, well, how do you know those spikes? How can you say that one of those spikes is definitely Thera? I am basing this on the fact that the geological estimates say this was an explosive eruption, a VI7. It went 36 or so kilometers into the stratosphere. I think the ozone layer is at about 20 at the latitude of Thera. So this definitely got into the stratosphere. Everything that came out of it, it went up, and it would definitely have got into the stratosphere. So if there's any sulfate in it at all, it's gone stratospheric. It should be deposited in the ice. It's logical. So for me, I feel comfortable to say that we should be able to see Thera in the ice to some degree. But it's any of these smaller ones would actually be quite consistent with what we know about the sulfate for Thera. So let's look at these data in a slightly different way. And so here we're just trying to do a little bit more. And what we did was we looked at, so when a volcano erupts and it puts out its sulfate layer, and you look at those patterns in Greenland and you look at them in Antarctica. Ooh. I think the museum is closing. Sorry, excuse me for the interruption. So we look at the last 2,000 years, and we look at where known volcanoes have erupted. What latitude are they at? What time of year have they erupted? And then we look at the ice. How does an eruption at this latitude look in the ice? What pattern does it give in terms of distribution? And on that basis, we can split these volcanic events across the Thera period. So these are just these spikes below, but now they are presented in the size of the bubble is showing you approximately how much sulfate is present. And I've arranged them by latitude. So this gives us a few more clues. So let's just, we've also got some of the archaeological date ranges. And again, it would take me a whole extra career to thoroughly understand and do justice to all of the different archaeological arguments. So I present a range, and I'm also presenting a range of radiocarbon because I truly think you could find a way to model radiocarbon at the moment to support any of these dates. I don't have a problem with radiocarbon not supporting any of these dates. In fact, I think that it does. So I'm very comfortable with that, but that's my personal opinion and that is subjective. And I'm also open to being proved wrong and happy to be. So let's remove these first two events because we know they're not Thera, right? So they're off the table. We can also remove this one. For the moment, there is volcanic ash associated with this. The geochemistry that's been done on this volcanic ash, they actually ruled out Thera about a decade ago based on geochemistry. Also, the latitude, it appears to be a very high Northern Hemisphere eruption. So we can get rid of that one. Good. And then moving down, we've got a Southern Hemisphere event. And we can remove that one based on what we know. It appeared to be very strongly a Southern Hemisphere sulfate. So then that doesn't leave us with too many options. And we've all heard many really excellent presentations talking about, for example, how Thera needs to happen after the start of the New Kingdom. We've heard, just a whole array. I'm not going to get too far into the archaeological evidence, but I would say from my understanding of the archaeological evidence, and for me, I'm pretty convinced it's not this one. I'm also, this in terms of the ice, this requires further work. In terms of how it shows up in the ice, it appears to be tropical, but there is just a possibility that it could be Northern Hemisphere. So I'm really keen for more work to be done on this event so that we can either confirm or deny for this one. And then we've got these others. And I'll look at this one. And I need to say something important about that one. How many at a time? Probably not well. Yeah. Okay. Okay. Right. So we'll have a quick look at this one. So 1561, there's actually this punctuator. We've got 1558 and 1555 here, and they're all separate sulfates. And again, this is a time period that is now, the whole of this time period is under closer study to try and get better resolved data. And what I haven't said so far is this one, 1538. So this is circa 1538. After this point, the ice becomes very brittle in the records that we've had access to so far. And the brittleness of the ice means we can't apply the dating based on a count of the ice layers. And so the dating for this one is not precise to one calendar year like the dating for these others is. So this will change. Hopefully we'll be able to get better ice and this will change. And it's where Malcolm's 1524 becomes relevant, because we haven't been able to look properly in the ice to see if there's a 1524 sulfate. I'm sure there will be a 1524 sulfate because the trees tell us there is one. Again, that doesn't assume that it's Thera, in the same way that what I'm going to show you now doesn't assume that this one is Thera either. But I want to show you this very, very quickly. So there is an Aegean dendrochronology record that I think you're probably all quite aware of, Peter Cunningham work, the master chronology from the Midas Mound tumulus at Gordian, which was downwind of Thera, about 400 kilometers. These trees were growing probably in the Taurus Mountains at the time of the eruption. And when we started doing our annual 14C on calendar dated bristlecone pine, a new opportunity presented itself, because this Gordian sequence, which has felling dates for Gordian and also interlinks with a number of other sites across Anatolia through the tree ring record, every time a new calibration curve came out, this whole thing moves forward in time 10, 20 years, backwards in time 10, 20 years. And every time it moves, and then you have to rejig all your associated chronology. And it's just not good enough. You know, we're tree ring scientists. We need to try and get this thing pinned down to a single year. If we can't do it by conventional methods, well, perhaps we can use, instead of tree ring widths to match our patterns, we use radiocarbon in single tree ring years to match our patterns. And that allows us to fix Gordian, which is what we did. The red data points are Gordian, and they're fixed by wiggle matching. There's an event in here that we were able to use. And so we now have this locked down, and it will not change again. The dating for Gordian will be fixed because it doesn't matter about a new calibration curve. We're not using a calibration curve anymore. We are using annual 14C. Anyway, having done all that, something became apparent, and it was this scan that I had run previously on the Gordian sample had revealed a chemical anomaly. And at the time I did the scan, it was approximately dated with the decadal wiggle matching technique. And then when we got it clearly dated, we found that it lined up with 1562. So here we have a chemical change in the trees at Gordian, 1562 to 1558 BC, which is exactly where that sulfate for that time period shows up in the ice. So I think there's probably a causal connection, but again, it's just based on coincidence and I can't prove it, between a volcano and this. It could be because a volcano puts out a volcanic pollutant. We know there was one. Do we know it's Thera? No, we don't. We can't prove it from this, but it's a possibility. Sophula Cave was mentioned yesterday. Sophula Cave also has a chemical change in it, currently dated around about starting around about 1628-ish. And the idea with this was that it begins and then it sort of dissipates through the cave system. And so I would say the dating for this is uranium series dating. Here's one uranium series date, here's the other. Then we've got an age depth model, and that's how the dating for this signature is done. It would be very interesting to see this reevaluated, because I know the Gordian sequence is ±1, and we have a chemical change, and this sequence I think might have rather more plus or minus on it in terms of the shift. So it'll be interesting to see what happens in that with that going forward. So, okay, just in summary, what do I want to say? I want to say, keep an open mind about Thera. I think by combining evidence from the archaeological record, radiocarbon where we can, using proxy records like this multidisciplinary approach, and increasing dialogue with each other, I think Thera can be solved to an exact calendar year. And I hope that this will happen while I'm still employed and I'll get to know about it. So thank you very much for your time.
Thank you very much, Charlotte. I mean, the things that I've got from it, I'm not talking about the data, I'm talking about your impartiality, which is quite impressive, as well as the great care, and that you're open to all possibilities in almost every method of dating. And that combined makes it, brings together something which is extremely positive and forward-looking, and so at some point I'm sure you will, and with the help of others, achieve this goal. So can I open the floor for questions directed at Charlotte, and we can also, of course, discuss Thera in the final discussion, which will immediately follow this as well. So, Malcolm, do speak.
Charlotte, first of all, thank you for that really splendid summary of your work. I'd like to bring you back to things we've discussed before. As we've said, the 1538 plus or minus 7 or 11 or whatever it is could, of course, be 1525. I'd like to begin by pointing to the direct evidence of the eruption. There have only been two, as you pointed out, two number 7 eruptions in all of recorded history. One was, of course, Tambora, and the other one was Thera. And an eruption of that magnitude would have to leave direct evidence in tree rings. And of course, we have the very direct evidence in the trees in California, Nevada, and Northern European Siberia and in China of 2 massive events. one at 1815, 1816 AD, the great eruption of Tambora, and the other at 1525, 24 BC, 2-year event, which appears in, and it's the only such event that appears in the tree rings in, as I say, northern China, northern Siberia, and the California-Nevada border, which is very direct evidence of a major eruption at that time. Then, of course, before I come to the archaeological evidence, there's the physical evidence of the pumice, because we would all agree that eruptions produce not only tephra, but pumice. And the Theran pumice is very noticeable, it's very identifiable, and it nowhere appears before the reign of Thutmose III. There are 19 examples of earlier pumice, all of them, as we've discussed, identified as coming from the earlier known eruptions in the Dodecanese, except for the one piece traced to Etna, which either floated or, as you pointed out, may have been traded all the way. But the Theran pumice only appears in these much later contexts. And then, of course, there's the archaeological evidence. One can play games, and many have, trying to stress Egyptian rain lengths, but you've got the testimony of the 8 officials who give you their entire biographies of, and if you stretch it too far, they end up serving 120 years, which no one in his right mind can accept. So these are basic facts which one has to deal with. And so I would come back to your 1538 plus or minus 11 date and focus on that, since the other evidence is overwhelming in favor of that date.
Well, I thank you, Malcolm. I know currently there's, I think 2 ice core teams are working on 16th century, and hopefully it will be possible to find some ice that is not as brittle, and that it's easier to get a more, because I think we've got to have that last part of the 16th century in highly resolved data to complete the picture. What I will say is we looked in the Antarctica, and in the Antarctic record there was no, you would expect Thera to show some register on both sides of the globe based on the explosivity. You would expect whatever sulfate was present, you would expect to see it in northern and southern hemisphere. And there's nothing big in Antarctica, but actually that doesn't necessarily mean that there's not something still hiding in Greenland, because as we looked at, as we sort of discussed this actual, how much sulfate Thera produces is really, really critical, because it is the thing that's going to determine how much it influences the tree ring growth. And at the moment, it's a bit of an unknown quantity because the petrography really can't describe it well enough. There've been some really nice studies where they've done sort of modeling at 2 ends of the range of sulfate production, but it's very wide ranging. So I think that's one of the things we really would be brilliant to be able to narrow that down, because it would also speak to your observation of the 1524 tree ring event, which, as you say, is compelling evidence for a major volcanic event, possibly too high a sulfate for Thera. That's the only thing. Because it is the strongest, as you say, it's the strongest marker in the 16th century in terms of the tree rings. That suggests a reasonably high sulfate event. But we just need, I think we need to keep searching the ice as highly resolved as possible and see what other data can be found. And, hopefully tephra, I mean, that this is the way to solve the problem once and for all, is if they can, my ice core colleagues can find tephra associated with one of those acidities that can then give us an exact, that is the thing that will really, really clinch it for me, at least, if they can show me geochemistry which matches. So
it is fascinating that all the ice cores and everything else are broken at exactly 1525 BC.
I know, it's like
as you pointed out, there's even the possibility that the magnitude of the Theran eruption was so great that it shook up all the ice cores. In fact, we don't have any of that data, unfortunately.
I know, it's like something is conspiring against us, because also a very important eruption on a massive radiocarbon plateau. So yeah, but maybe one day it will be solved.
Can I ask a question?
Yes.
I mean, partly it's also what I said yesterday, the micromorphology for Egypt, that would help a lot if we could have stratigraphical information with tephra present rather than pumice.
Yes.
Pumice, I don't know. But the other question is, I mean, these big spikes that you showed, like in the 17th century.
Yeah.
We should have like some
They should,
bad impact.
right, they should show up. They should show up.
Yeah, well, climatic, social, so I'm not sure. I was thinking, what can we pinpoint in the 17th century that?
Yes, I think that's a very good question. And I'm sort of looking at the juniper trees. So again, full disclosure, there's an argument about how solid our Mediterranean juniper chronology is, with a bridging chronology from a site called Porsuk, which has a signature. And Sturt's argued that moves that dendrochronological match is not valid based on radiocarbon. I quite like the dendro match, but I agree. I mean, it was never a very good dendro match. So, but with everything dated as it is now, the growth anomaly, which would indicate a really wet phase in the Mediterranean, is bang on 1654, which we now know there's a great big volcanic eruption that happens in 1564. So it makes sense. Again, all of these things are open to question. But I think that's a really cool research topic that you just mentioned. It's perfect.
Question?
Does anyone else have a question just now?